So you may recollect that we were developing the formulation for the for a plain beam member we started with. So basically we put these kind of restraints at both ends, which is basically suggesting that it's a beam because it's not allowing any vertical movement here. There was P axial force acting, there were bending moments acting, and there was shear force which was coming out of because of these. And we assumed that there was no force acting in between. That can be taken care of separately, as you are already familiar. So the loads can be only acting at the nodes here, as far as this formulation is concerned. And then what we did was we tried to develop an equation for mz everywhere. From that mz formulation, we developed the deflection, and then we developed the formulation for v prime, that is rotation. And that basically the idea was we wanted to relate these rotations at the ends with the forces at the ends. So we wanted to relate θ1 or θ A and θ B with MA and MB. Now for a linear problem, as we had discussed, I think this is where we had stopped, somewhere here. So for a linear problem, we already know that if it's a beam member, let's say, so moment at one end will be 4 EI by L times rotation at that end plus 2 EI by L times rotation at the other end, right? You're all familiar with this idea. 4 and 2, right? So 4 EI by L is the rotational stiffness of any beam member at that joint itself. And the other end, if I introduce the rotation of θ B, then at that joint, because of that rotation θ B, I will be having a moment demand of 2 EI by L multiplied by θ B. Correct? This everybody is familiar with, right? You have understood this very well. We developed the formulation for a geometrically nonlinear beam member. So in case of a geometrically nonlinear beam member, since it was deforming, right? So the rotations at the end, so if I apply a moment here and there was axial load applied, so because of the presence of this axial load, for a given moment, I was supposed to get a certain theta for a linear member. But for a non-linear member, I'll get a larger theta. You follow me, right? There is an amplification factor. Correct? So that amplification factor, when we derived that equation, we did not get the amplification factor separately. Basically, it got all pretty complex. Actually, the equations were relatively longer, and what we got was an equation like this: MA is equal to EI by L SII theta A plus Sij theta B, where SII and Sij are given by these equations. Likewise, MB was equal to Sij theta A plus Sjj theta. Sij is this one, Sjj is same as Sii, which is given by this one. So there are terms of sine and cos KL, KL. What was KL? Anybody remembers? What was KL?
So K is square root of P by EI.
Correct, very good. So basically what we had done some substitution along the way. What we had done was K was taken as square root of P by EP divided by EI. Okay, so KL will be this L multiplied by square root of P by EI. Or in other words, we had substituted P is equal to K square EI. Okay. So that is K. The K here is not the effective length factor. Don't confuse that K with this K. Okay, it may turn out to be that way, but right now we are not. No, that's not the same K. Anyway, so where was I? Yeah. So we got this as the stiffness coefficients, right? And if you compare that with the stiffness coefficients that are, or stiffness metrics comes for a linear system, we used to get this one, which we had derived from flexibility method in the very beginning of this course. Okay. So now the two can be compared, but the problem is that we cannot. There are terms of sine and cos here. So one way to find the values which are similar to these is to write a Taylor series of this one. Another option could be and then write a Taylor series, take some of the important terms, initial terms, and ignore the higher order terms for small values of KL. So basically K represents your axial force value, right? K is basically equal to square root of P divided by EI. So it represents axial force value. So higher the K, higher the axial force. Right? So one way could be that. What I have tried to do here is I have basically just substituted some values of KL into these terms. So on the horizontal axis, you see the values of KL. On the vertical axis, you see the values of SII in this plot. You can see this plot?
Yes, sir.
So,
Yes, sir.
so you can see that as I reduce the value of KL, I start from a value of 4 and then I keep reducing. I divide by a factor of 1.5 in every single step. And as I keep reducing the value of KL, the SII value converges towards 4. You can see it. Likewise, the SIJ value starts from something like 3 when the KL value is 4 and then converges towards 2. Follow me? So as KL tends to 0, the SII value tends to 4 and SIJ value tends to 2. And KL tending to 0 means what? Your axial force tends to 0. So when the axial force tends to 0, then you are not going to have any coupling between the axial force and the moment because axial force is not there, right? So which is basically same as your linear problem, right? So this is basically a special case of this formulation. This is the case where the P is not affecting the deflection, the lateral deflection. But in this case, we are including the effect of axial force on lateral deflections or rotations. Got it? However, you cannot simply substitute the value of KL in these equations because you will get 0 divided by 0, which you cannot solve. Okay. You can alternatively take a derivative of the numerator and denominator several times with respect to KL. And then you will see that after a few steps, after taking a few times those derivatives, the denominator and numerator will stop giving you 0 divided by 0. And then you can substitute the value of KL is equal to 0 and get the limit. Okay, that is L'Hospital rule. Fine?
Yes, sir.
Yeah. All right, so moving forward. Did we do this part also in the previous class? I cannot recollect. So basically what we have derived in this step here is MA as a function of theta A and theta B. So basically we had, in the previous step, we had derived theta A and theta B as a function of MA and MB. This formulation was basically theta A is equal to something multiplied by MB plus something multiplied by MA. Then we solved it to reverse the order. So here we had theta A and theta B as a function of MA and MB, but you can solve for MA and MB in terms of theta A and theta B. So that we did. Then we took EI divided by L out, and then we got these two stiffness matrices, these two terms, these 4 terms, which are essentially 2 terms. Okay. So these are relating MA and MB with theta A and theta B. As we know that P in itself is not affected by, or the axial deformation in itself is not affected by the rotations. Now that may not be absolutely true. If you go to a even higher order analysis, you will see that as the member deforms like this, even axial deformation is affected by that, but we are ignoring that effect. Okay, so what if you ignore that effect? Then what you can do is P is equal to axial deformation multiplied by AE by L, right? So P is equal to AE divided by L. If you multiply EI by L multiplied by A by I and I will cancel out. You will be left with AE divided by L multiplied by axial deformation. Okay. So here, what assumption are we making? We are making an approximation here when we say P is equal to this much, where it does not depend on theta A and theta B. Sorry. Somebody has to say something. Should I explain what I'm asking, or you guys understood what I'm asking?
Yes, I understand.
So what was the assumption that I made?
So the axial thing is not coupled with the that moment part. Means,
No, that's a very generic statement, and that may not be true. See, some parts of axial behavior. So when you apply P force here, it is introducing a moment demand here, and that is increasing the value of theta. That coupling is happening in this formulation. That is why you have SII, SIJ terms. Instead of 4224, you have SII, which are different from those ones. So it is not that P is completely uncoupled with the flexural behavior. P is not uncoupled with the flexural behavior. That was your linear behavior that we have already studied before. They are coupled now. What is uncoupled is this, still, like, it's not fully coupled, you can say. So what is happening is that because of theta A and theta B, ideally, if you take a member and you deform it in flexure, you introduce a theta A and theta B, you would automatically have a reduction in the axial length, right? So because now the member is having to traverse this length, it will move slightly in the horizontal direction, in the axial direction also, right? So your E should depend on theta A and theta B. Or in other words, E should depend on MA and MB. But that does not happen in this formulation. So your theta A and theta B depend on P. Theta A and theta B depend on P. That kind of coupling is there. But your E does not depend on MA and MB. E depends solely on P. So this is not a fully coupled problem. I'm not really we have not formulated the problem with full coupling. It's still partial coupling only. Okay, so it's a very approximate solution. It's not a 100% perfect solution. Okay, but we know obviously that the effect of P on this lateral deformation is much more significant. It has a more significant consequence on the member stability than the effect of MA and MB on E. Okay, so that's why we can ignore it for a while. So in this formulation, we will continue to ignore that effect. Fine. So as long as we ignore that effect, we can write the formulation this way: P, MA, MB. P is the axial force, MA is the moment here, MB is the moment here. That is some kind of a stiffness matrix here that we have discussed already in detail, multiplied by E theta A theta B. E is the axial deformation, theta A is rotation here, theta B is rotation here. Okay, fine. Now this is pretty much solved. Now only thing that is left here is that this formulation is done for a beam, plus the way we are defining our degrees of freedom, E theta A theta B, are not consistent with the way we have been defining our degrees of freedom before. If this was a beam member, what would have been the ways we would define the or it's a frame now because we have introduced E now, so it's a frame member now. So what would have been the degrees of freedom for a frame member, plane frame member? How many degrees of freedom it would have, a plane frame member?
6.
6, right? 3 here and 3 here.
Yes, sir.
Axial movement, lateral movement, rotation. Axial movement, lateral movement, rotation. What I have got here is only 3. Okay, which in a very nice, in a nutshell, in a way, it includes all those things, but still, so for example, E here relates axial deformation here and axial movement here and axial movement here. That is, E is the deformation, which is basically a difference of axial movement here minus axial movement here. Agree? You agree?
Yes, sir.
Right. Likewise, if you see theta A is, if you look closely, theta A is the rotation with respect to this axial line. Right? In a frame formulation that we had developed before, that was not the theta A theta B value actually. So this may be okay as long as it is not swaying. But let's say if it starts to sway, then instead of being horizontal, this member goes this way. So in this formulation, your theta A, let's say, member deforms this way. Your theta A will be which angle? This angle. If I can draw this tangent here, or let me, 1 second. Theta B, it will be this one, right? This is theta B. That's how you are defining your theta B. But in the earlier formulation that we used to deal with, we used to define theta b with respect to not theta b actually, this degree of freedom with respect to the original horizontal line. So if you want to say d1 to d3 here and d4 and d5 and d6 here, so this would be d6, correct? So d6 would have been this rotation, not from the secant line. So if you call it secant line, this is the line that is straight line that is joining the two joints or two nodes. So that is the secant line. You did not measure your angles from that line. You measured the angles from the original point of reference. The original point of reference was this one. So that would be the d6 value. Agreed? So there is a difference in the way we are measuring the coefficient. So basically, theta A and theta B do not really, E theta A and theta B do not really represent the movements in the degrees of freedom. These are more of internal deformations, okay? And we have to relate them with the actual degrees of freedom, which are marked like d1, d2, d3. So d1 will be movement in this direction, d2 will be this one, d3 will be rotation with respect to this horizontal line. Similarly here, this movement, and this rotation, okay? That's how we will define d1, d2, d3. Anyway, so that is one part missing. The other part that is missing is on the force side. So if you look at the force side, I have only one axial force value, just like here, just like in the displacement side. What I have is I have only one axial force. But actually, when we developed the stiffness matrix, we did not have one axial force. We would have one force acting in this direction, one force acting in this direction, in each degree of freedom. So even these values, should be corresponding to each degree of freedom rather than just the axial force value. Okay, so basically you should have, if there is an axial force P acting, you should have a term of A1 to A6, where you had P for A1 and you had A4 somewhere where you would have minus P. Agreed? So instead of these three terms, you should have these six terms where the first and the fourth terms will be P and minus P. Likewise, the second term can be MA, the third term can be MB, and so on. Fine, you follow me, right? What we are saying? Sorry, second term will not be MA. I'm sorry. Second term will be corresponding to the shear force. So now if you look at the shear force, if I go back to the original formulation, you remember this formulation where we had applied MA here. So the shear force at this joint, at this location, lateral force, was MA plus MB by L. So that will be, if this is the first degree of freedom, this is the second degree of freedom, this is the third degree of freedom, then the second degree of freedom force value will be MA plus MB by L, minus or plus. Here it will be minus, plus, here it will be minus. Fine. So that will be the force in the second one, which is basically a function of MA and MB again. Right. So let me go to Notepad and so to recap quickly what we just discussed. This was the beam element. We derived an expression for the member that has MA, MB, MA plus MB divided by L, A plus MB divided by L, and a P force acting here. We derived an expression for this P, MA, MB. This was a function of some kind of a stiffness, okay, E, theta A, theta B. And how were E, theta A, theta B were defined? E is the axial deformation. So initially the member was this long up to here, and then it has shrunk to here. That is your E. Fine. And with respect to this line, which is the secant line, we will call it theta A. And with respect to this line, we'll call it theta B. Fine. And this stiffness matrix was basically SII, SIJ, SJI, SJJ. Fine. Then the challenge here is that this foundation is fine, but this does not really help me work with the to really solve a problem, because when we have a large matrix, we have to assemble the stiffness matrix, etc. So we have to deal with the actual degrees of freedom. So the real degrees of freedom, if you may see, this member originally may be here, but after deformation, let's say it moves and it goes there. Okay. And then this is the secant line that I've just drawn. And then with respect to the secant line, the member will have these deformations. Again, we will call them theta A. We call it theta B. The degrees of freedom that we traditionally deal with would be D1 in this direction, D2 in this direction, and D3 in this direction. Correct? Similarly, you would have D4, D5, and D6. Okay, I'll just erase theta and theta before I write. That is drawn anywhere up there. Okay. So what we need to do is we need to find the stiffness matrix which deals with A1 to A6, which is the force vector. Some kind of stiffness matrix needs to be there, which will relate my D1 to D6. Okay. Fine. So let's try this. So we need to relate two things. We need to relate P, MA, MB vector to which vector do we need to relate it to? So this was that vector, P, MA, MB. And we need to find what is the relationship between P, MA, and B to A vector. Isn't it? The class is very quiet today. You agree or not?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
And we need to relate E, theta A, theta B to D1 to D6. Correct? So let's deal with this problem first. So we know that E would be equal to D1 minus D. Which one? D1 minus? E will be equal to how much? D4. Correct. And theta A will be equal to, in this particular case, this is your theta A. But we have to relate it with D1, D2, D3, and D4, D5, D6. What will it be equal to? If you see, theta A is nothing but d3 minus this angle, right? d3 is this full angle from the horizontal. This is the horizontal line minus this angle. And how much is this angle? What is this angle? d2 minus d5 divided by L. Likewise, theta b will be equal to d6 minus d2 minus d5 divided by L. Okay, so this whole thing I can write in this form: E theta A theta B is equal to d1 to d6. Okay, so E is equal to d1 minus d4, right? So I should have 1 here, and then at 4th degree of freedom, corresponding to 4th degree of freedom, I should have -1. So second, third is 0, -1, 0, 0. Is that correct? Likewise, for theta A is nothing but d3 minus d2 by L. So there's no term related to d1. Then I have term related to d2, which is -1 by L or -1 by L. Then I have 1 corresponding to d3. Then no terms corresponding to 4. With respect to 5, I have -1 by L again. Sorry, 1 by L actually. And 0. Likewise, theta B will be 0, -1 by L, 0, 0, 1 by L, 1. Okay, so I have related my deformations. These are the deformations with the displacements. Displacements in the degrees of freedom. Subsequently, I also need to relate P, MA, and MB with the PMA and MB in a way are internal forces, so to say, which I want to relate with the forces in the global degree, in the member degrees of freedom. So let me draw this, or let me copy paste that diagram. So there is a force P acting here, and there is a force P acting here. This distance we can call delta, the vertical distance or lateral distance between the two joints. Okay, that is basically your sway value. Okay, so there will be an MA moment acting here, and there is an MB moment acting here. Okay. Now we had already seen that because of this MA and MB, there will be lateral forces acting here to keep MA and MB in balance. Now what you would see is that if there is a sway, even the two P forces are not balancing each other, right? There is an unbalanced moment because of the two P forces if there is a sway. And as a result, first you will have MA plus MB divided by L. In addition to that, you will also have P delta by L. Do you follow? See, the MA and MB, they are, I'm assuming, both clockwise. So MA plus MB is in the clockwise direction. So MA plus MB divided by L will be the force required, and this, the net force here, is in this direction, right? In this direction. So but there is net force here and there is net force here. Shear force here. So this shear force is MA plus MB by L. That will balance this and this combined. And in addition to that, if you see the two P forces, they are also making the member rotate in. They are making the member rotate in anti-clockwise direction, right? The two P forces, they are creating an imbalance in the anti-clockwise direction. So therefore, a negative sign here. P delta by L. Okay, and this is this delta. So P delta is the moment and divided by L, so that you get a lever arm for this is the length. Okay. Likewise, at this end, you would have MA plus MB divided by L. This was already there. Earlier also it was there. But because of the sway, we will have now P delta by L. Okay. And delta is given as D5 minus D2. Right. So this is D5. This is vertical movement D5. And this is vertical movement D2 at this degree of freedom. And that delta goes into this equation to give me the lateral forces. Right? So these lateral forces are nothing but in the A vector, A1 to A6. These are basically A2 and A. This is A2 and this is A5. Okay. Now, we will deal with these two parts one by one. So this part holds true even if there is no sway. Similarly, this part holds true even if there is no sway. When there is sway, then this part comes in. So we will not bring in this second part yet. We will only deal with the first part first. So what do we want to do? What we were trying to do here, we need to relate P, MA, MB as a function of some kind of a relation matrix, A1 to A6. That's what we want to do now. Yeah. So let me write A1, A2, A3, A4, A5, A6, which is equal to some matrix multiplied by P, MA, MB. Okay. So A1 is basically in the same direction, which is the direction of P. So what should be the coefficient here? A1 is equal to what multiplied by P? First of all, how many columns will there be in this matrix?
3 columns.
3 columns, right? Because we have to multiply with 3 terms here. Okay. So what value should come here? A1 is equal to how much? P is in this direction.
0.
Oh, 0. 0 multiplied by P is A1.
1, sir.
Yes. And 0 multiplied by MA and 0 multiplied by MB. Fine. A2 is this one, A2. Okay. Which is basically, A2 is in the upward direction, but the force is actually acting in the downward direction. So, and I'm ignoring this part so far for the time being. I'll come back to this again. So this part does not have to be included, only the first part, that is non-sway part. So A2 is, because of P, there is no A2, because I'm ignoring this part. So let me write 0 here. Okay. Because of MA, it is 1 by L, but in the opposite direction, so minus 1 by L. And because of MB, it is minus 1 by L. Agreed? So A2 is equal to minus MA plus MB by L. Likewise, A3 I can write. A3 is nothing but MA. Sorry, A3 is nothing but MA. So 0, 1, 0. Agreed? Likewise, we will keep going. Minus 1, 0, 0, 0, 1 by L, 1 by L, 0, 0, 1. Fine. That is PMAMB. So now I have related the 6A vector, 6A component with P and MA and MB. But for this part, I was ignoring this. But anyway, we will hold it. Now, as I had mentioned before, we need to connect A1 to A6, this A vector, with ultimately the D vector. But what we have just found is, let me call this matrix alpha. Okay. And let me call this matrix that was relating displacement side of it beta. Okay. So I found A1 to A6 is equal to alpha times PMAMB vector. Okay. Which I knew was equal to, what was PMAMB equal to? This thing right here. Alpha matrix multiplied by EI divided by L. What was this? A by I, 0, 0, 0, 0, SII, SIJ, SJI, SJJ, multiplied by the deformation vector, E theta A theta B. Also, I know, I just derived, E theta A theta B is equal to beta times displacement vector, right? So I can substitute that here. So this one is basically beta times the displacement vector. So now I've got force vector, which is equal to alpha times this stiffness matrix beta times the displacement vector. So I'll call it this whole thing as stiffness vector, stiffness matrix times D1 to D6. Okay, where S is equal to, I'll take EI by L out, alpha times whatever, A by I and so on, SII, etc. times beta. Okay, if you multiply these alpha and beta values to this matrix, I'm not doing it here. What you will get is matrix. Okay. So after doing that multiplication, you will be ending up with A is equal to this matrix multiplied by the deformation matrix, deformation vector. Okay, so you can see that you got the terms of A by I, which were there. You got terms of SII, SIJ, and in fact, if you look at the rotational degree of freedom, the rotation is basically equal to SII times the, in other words, moment at each end is equal to SII times D3. Right? So the rotation and moment are still related the same way as they were. But now, since you have got some additional deformations, additional displacements added, you got terms of SII plus SIJ added together. Okay. So this is your new stiffness matrix, but here still we had assumed that there was this component was ignored still. Which component was that? P delta by L. This P delta by L is corresponding to sway. Okay. So this is the geometric nonlinear, I would say, stiffness matrix, including the effect of geometric nonlinearity, including the geometric nonlinearity for a non-sway frame member, plane frame member rather. Okay, so it has geometric nonlinearity effect, but only within the member. So the two ends of the member are not moving laterally. They are still, if the P is acting this way, these two members are not moving laterally. That movement is not there. But in between there can be movement, and that movement will introduce some non-linearity, and that is incorporated in this formulation. Follow me? However, we had almost developed that formulation, but we just ignored some part of it. If there is a lateral movement, then there will be this P capital delta effect, which is called capital delta. This is capital delta. There will be this P capital delta effect that we need to, which was written as P delta by L, if you remember. Here I had written as P delta by L, that is P capital delta effect, that we need to introduce or add to our formulation. And what was happening? Where was that P delta effect coming in? Into the force that is acting in the second and fourth degree of freedom. This is the second degree of freedom, this is the fourth degree of freedom. In these degrees of freedom, some lateral force was additionally there. So that P delta by L and P delta by L, we can add, or we can write it in this form. So this is, let me copy paste that S matrix here. Let me see if I can do that. So this is my S matrix. This is without the sway. If you want to include the sway value, you should notice that only thing that changes was in A1, A2, and so on. There is A6. Only thing that changes are A2 and A4 values. Not A4, sorry, A5, I think. I'm sorry, I think I misspoke last time. It will only change the values in 2 and 5th degree of freedom, right? This is the 2nd degree of freedom, this is the 5th degree of freedom. So only those lateral forces will change. So what I can do is, in the same stiffness matrix, I can simply add the terms corresponding to the 2nd and 5th degree of freedoms. So I know that A2 is, the sway term will be, let me draw it again. There is P force acting here. There is P force acting here. There is minus P delta by L. This is the delta value. Okay. Delta is nothing but D5 minus D2. So there will be a lateral force. If I'm showing this lateral force in the downward direction, then it is P delta by L. Otherwise, I can show it in upward direction. Then it is P delta by L. And there will be a downward force of, because if you see, these two P forces are basically making the member rotate in the anti-clockwise direction. So the P delta by L has to be such that it makes it rotate in the clockwise direction. Okay. So these will be the forces, P delta by L and P delta by L. Everybody agrees with this? P delta by L? Yeah. Right? Yes, so my A2, the additional A2 is basically equal to P delta by L, which will be equal to P D5 minus D2 by L. And A5 is 5th, right? Yeah, A5 will be equal to, since it is in the opposite direction, downward direction, I'll call it minus P delta by L. That will be P D2 minus D5 divided by L. Okay. So now I've got the additional terms of A2 and A5 in terms of D2 and D5. Okay. So the additional stiffness matrix, that is for sway, this additional A1 to A6 will be equal to, A1 is not affected. So A1 is equal to this, and there are 6 terms here. Right? So A1 is not affected, so it will be all zeros. A2 is affected because of D5 and D2, right? So minus P D2 by L. So minus P by L. And then the fifth term, that is P by L. Okay. The rest of it will be 0. D3 is not affected. D4 is not affected. D5 again is affected. How? It has an additional P by L in the second degree of freedom, and that it has minus P by L in the fifth degree of freedom. Okay. Then D6 is not, A6 is not affected. So this will be your additional stiffness matrix because of sway. Additional stiffness matrix due to sway effect. Okay. So now what I can do is I can combine the two. I can combine the earlier stiffness matrix. So if you notice, where are the terms? The terms are only at 2, 2, 2, 5, 5, 2, 5, 5 at only those locations. So 2, 2 term is here, right? 2, 2, 2, 5, 5, 2, 5, 5. So these terms will have an additional value of minus P by L, and so on. So what is P by L in terms of KL? So P divided by L, P was equal to how much? We discussed that K was equal to square root of. Agreed?
P by A.
Yeah, so P is equal to K square EI divided by L. Okay. So if I do that, so minus P by L will be equal to minus K square EI. I just add those terms to this stiffness matrix. What I get is, can you see my screen? So earlier we had this term of 2 SII Sij divided by L square. That was without the sway effect. With sway, I'll bring in this minus K square term, basically. Right? EI by L is already outside, minus K square term. EI by L is taken outside, so minus K square term, which is what I've got here. Okay. Likewise, the term 2, 2 is affected, 2, 5 is affected, which will have K square L square. 5, 2 is affected, and 5, 5 is affected. So they have additional terms of plus or minus K square L square. Okay. So this is the total stiffness matrix, which includes the effect of non-sway and sway both. Okay. So basically, this is the generic matrix. If you don't have the sway effect, you can automatically, it will take care of in the D2 and D5, because D2 and D5 values will be same. So let's say so this is the sway effect, right? So this was the stiffness matrix that takes care of the sway effect. So if D2 and D5 are equal, that means what is the sway? What is delta?
Delta will be 0.
Delta will be 0. That means sway is not there, right? So when the sway is not there, what will be the terms here? What will be the A2 value then? If D2 is equal to D5?
Those things will be 0.
0, right? Because minus P by L D2 plus P by L D5, they will cancel each other out because D2 and D5 are equal. As a result, you will not have any additional forces coming in because of sway effect. But if there is a sway, that is D2 and D5 are not equal, then the additional terms of A2 and A5 will come. All right, so you got the total stiffness matrix, which includes both the sway and non-sway effect. Now you can use the same stiffness matrix for non-sway cases also, because automatically it will adjust for that. Fine. Now, this stiffness matrix is a bit complex, right? And the thing is that when you want to do develop a linear solution, you go for that stiffness matrix, which you are familiar with here. This kind of a stiffness matrix you are familiar with, BI by L, AI, 12 by L square, 6 by L. And when you want to deal with a nonlinear problem, then you go to this kind of stiffness matrix, which has sine and cos, etc., to be accounted for. You can do that. There is no harm in doing this. Most of the programs nowadays are smart enough that they can calculate sine and cos and so on. So there is no harm. You can use this equation as it is. But it seems a little bit like completely two different solutions. one for geometric nonlinear problem, another one is linear problem. What people have tried is they have tried to expand the terms of SII and Sij, and these are sine and cos functions therein, right? Within the SII and Sij functions. So if you write the Taylor series and take like first two terms or first three terms and ignore the rest, higher order terms of those sine and cos functions, and then substitute the values, people have tried that, and what they got was they were able to separate the part of the stiffness matrix which is for the linear problem and the stiffness matrix which is for the nonlinear problem. So this one has been taken by, I think, taking first two or three terms of the Taylor series. I'm not 100% sure how many terms were taken. So basically this stiffness matrix, the whole stiffness matrix, can be approximated as a combination of or summation of these two stiffness matrices. This is exactly same as what you had for a linear problem, where the P did not have any effect on the or any amplification on the moments. Okay, so this is that matrix plus this matrix which accounts for the secondary moment effects. Okay, and this is applicable for both sway and non-sway conditions. If it is non-sway condition, automatically the terms corresponding to non-sway or the corresponding to sway will cancel each other out. Okay, here if you see the second part of this matrix has P as a multiplier. So basically, as you increase the value of P, the stiffness decreases. Right? So if you have a frame member, it has certain flexural stiffness. You keep increasing the axial force on this member, and its flexural stiffness decreases. Right? Which makes sense, right? Because at a certain P, it will lose all its flexural stiffness and it will buckle. Right? So that's what. So this can be an approximate solution or a good solution for matrices or for members which don't have a very large value of P, okay, which is not anywhere close to pi square EI by L square. Up to that limit or up to very close to that limit, you can use it. Not, I mean, up to certain distance from pi square EI by L square, you can use it. When P gets very close to the critical load value, then this will be very inaccurate. Okay, so one thing to notice here is that P value is to be entered in positive for compression. Okay, that's how it is developed. If the P force is actually in tension, then you would enter a negative value here, which will basically mean that overall stiffness becomes greater. So member becomes stiffer if you are applying P in tension. Okay, all right. So this this is where I'll stop. I think I've covered most of the points here. So total stiffness is basically a summation of, or can be written as in approximate manner. It can be written as a summation of your member stiffness matrix, which is linear stiffness, plus the geometric stiffness matrix. Okay. So for a member that is subjected to compressive force, this geometric stiffness will be having a negative effect on the original stiffness. Fine. All right. So this is where we will conclude this lecture and this class. I will try to share with you some example. Let me see if I can get somebody to solve the program, solve some example for me. I'll share that with you. Okay. Any questions? Or doubts about the project or the assignments or anything in general about the course?
Sir, when is the submission, sir? Project.
When is the submission? The deadline I had given was 19th, right?
Okay, sir. Like,
Yeah. How much time do you need? See, the thing is that first I have to grade, like after you guys submit, I'll need at least 1 or 2 days to grade the whole thing. Still, I'm grading the other assignments that you have submitted before. I'll need an additional 1 odd day to grade it. Then I have to send the scores to Professor MKM, and the two of us will sit together, decide the grade. So we will need 1 or 2 days for that. So 25th is the last date for submission of the grades. So instead of 19th, maybe I can give you up to 21st, but not beyond that. Is that okay?
yeah, sir. Fine.
All right. Anything else? How about some feedback about the course? How was this course? How was this pace of the instruction and course content? Was it too boring, too basic, too complex? I don't think anybody would say it is too complex, but feel free to let me know if you have some comments on the course.
Sir, I like the course, sir. A lot to learn.
Okay, good. Any improvements that you guys suggest? The way I can, some material that you might have found more useful that I should have shared, I did not share, or anything like that. Or some discussion I probably did not spend as much time, which I should have. Okay. Anyway, I mean, if you are not feeling like saying anything at this time, you can always write me an email, suggest, and of course, I would welcome it. So any suggestions or any feedback, good, bad, whatever, ugly, anything will do. Okay. So feel free to just contact me if you have any feedback or any other information that you want to share with me, which can improve the course, at least for future, right? So yeah, I've been teaching this course, I think, for 4 years now, but this nonlinear part that I have covered only, I think, some part of it I had covered in the Newton-Raphson method I used to cover in all this while. But this last 2 lectures, this I have added only last year. Okay. So unfortunately, I don't have enough time to give you proper examples with this. If I had that kind of a time available, then you would see how powerful this geometric stiffness matrix itself is. So I'll try to still give you an example. Please find time to go through it and see how effective it is to determine the. So for example, you guys know when a column will collapse, right? Just give me 1 more minute. It is just some informal discussion. So we have derived the expression for a column buckling, not V in other classes, surely, right? You can still see my screen, right?
Yes, sir.
Yes,
you
sir.
know when this column would buckle, you know the equation for this column buckling. But if I give you a frame, okay, like this, and I apply a load on this one, and there is no material failure, so material is strong enough, but the flexibility may be a concern, and this may buckle. If I ask you when it will buckle, how would you go about developing an analytical solution like you had developed for this case? Would be a nightmare if you have to develop an analytical solution from scratch for this problem. Okay, you understand that this frame can also buckle, right? These are all rigid connections, but still this frame can buckle. Right? If you apply large enough load, you will see that it will start to go laterally. Okay, but if you want to develop an analytical solution from the scratch for the entire frame, it will be impossible. But you can do that much more easily with this method that we have just developed. Unfortunately, I didn't have time to explain you or give you an example of this one. All you have to do is, we have got the stiffness matrix for each member, right? For the entire frame, you just need to assemble the stiffness matrix and solve it. Okay. You will have a numerical solution for you. So you keep increasing the load, axial lateral load. There are 2 ways to solve it. One is you develop the S global. You take the determinant of S global, make it 0. When the determinant of S global is 0, that means the stiffness matrix has become 0, or the system has become unstable. And for what value of EI, or what value of P rather, because your S itself depends on P. You will see that your S itself will depend on P. It will be a function of P. That is, this is stiffness matrix, right? So in this stiffness matrix, here you have a function P in the stiffness matrix itself. So you will see that. Sorry. So when S global, determinant of S global becomes 0, that means your P critical has been reached when the entire frame is going to buckle. So this is a very, very powerful scheme, and then you can even incorporate some level of material nonlinearity into this one and still predict the failure and so on. Okay. So most of the softwares, which especially for designing, I'm not talking about the softwares which are used for FEM, etc. But SAP 2000, STAD, and most of these softwares basically use this stiffness matrix, either this one or the previous one. This one. But when there is always a switch which you have to switch on to do a geometric nonlinear analysis, and they either use this matrix or this matrix. All right. Fine. So I'll still try. I don't know how much time I'll get to solve it. Give you a solid example. I'll see if I can get from a textbook. That will be easier. All right, guys. Thank you for your time. Thank you for being attentive listeners. Unfortunately, I would have loved it to teach in a real classroom rather than this one, but let's see. Okay. Next semester, I'm not teaching you any course. I'll only be teaching you undergraduate classes in the next semester. But stay in touch. Yeah. All right, guys. Thank you.
Thank you, sir.
Thank you, sir.
Yeah. Bye-bye.
Bye, sir.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you, sir.